Good morning. So we are continuing with our discussion on the MOS inverter analysis, which we started in the last class. Remember that. So this is an inverter which is called NELS inverter, and we are analyzing it. In the last class, I also gave you a problem, that for a computer, writing a small computer program for getting the output-input relationship. I do not know whether you have done it or not. It's up to you. We have seen that when the output voltage is near the high state, this transistor when the output is near the high state, what will be the condition of this transistor? This will be in when output is high, this transistor is always in saturation. That is why I have preserved. But what about this transistor? This I have called driver. Yes. So this is driver and this is load. This transistor, when output is near the high state, this transistor, the driver is in saturation, whereas the load is always in saturation. That we have ensured by short circuiting the gate and the drain. All right. Whereas when that output voltage is near the zero, that means near the zero state, this transistor then passes into linear region. When output is low, this VDS is low, means it is near this linear region. This goes into linear or non-saturation region, and we have to, as I have told you, that we have to write down the corresponding equations for load current. This is I called IDL, and this I called IDD, and this current which is sunk by the load, I have called it IL or I capital L. I assume that IL is equal to 0 in the steady state because the load is usually a capacitance. I told you that. IL means the load current. I capital L is the load current. We assume that IL is equal to 0 in the steady state under DC condition, because this output node goes to a similar input which is basically a capacitive input, as I told you earlier. And always we have assumed that in the steady state, the load transistor current and the drain transistor, the driver transistor current, they will be equal. So what we did, we wrote down the equations for the load current and the driver current, drain currents, under the various conditions, and obtained relationship between output voltage and input voltage. But instead, in our last class, there is a little error, as I remember. I told you that there was a little error. I told you that the borderline, where the condition that when driver is in saturation, this particular condition, driver is in saturation, this particular load is always in saturation here, the driver is in saturation. This has to be, to ensure this condition, what I have to do is the VGS of the driver, which is VI, minus the VDS of the driver, which is VO, should be less than equal to threshold voltage. This is the condition actually, and as a result, which shows that VO should be greater than equal to VI minus VT. I was writing PLAs because of certain confusion in the last class, which is wrong. Please note down, this is the condition. VO should be greater than equal to VI minus VT in order that the driver transistor is in saturation. Please remember this. Not VI plus VT, which I was writing in the last class. It was a wrong thing. Okay? Please take note of this. The driver transistor is in saturation means we are ensuring that this is ID versus VD relationship. We are ensuring that I am to the right of this line, somewhere here. This is a condition for, this is a region of saturation, for which the gate voltage minus drain voltage should be less than the threshold voltage. You remember the transistor, this is your transistor, MOSFET, N plus, the source and drain, this is P substrate, there is a gate oxide, and then there is a drain, there is a gate, you remember that, and we have got connection from here, this I called source, and connection for here, this is drain. And I told you that in pinch-off region, conduct pinch-off condition, the drain region, just at the drain end, there is no, at the drain end, no inversion layer exists. And that happens only when VI, the VGS minus VDS is less than VT. Then only you can get, at the same time you have to have the condition that this VI, which I must always mention, that VI must be greater than equal to VT. This condition must be there, otherwise the transistor will not be on. The input gate voltage must be greater than equal to VT. That is a must. At the same time, I have to ensure the other condition that VO, the output voltage, should be more than VI minus VT, so that a pinch-off region exists in the drain end. That means in the drain side, no inversion layer is formed. And that is ensured by the fact that VGS minus VDS is less than VT. So naturally at this end, therefore, there will be no inversion layer formed. And I think I've told you that under this condition, the entire drain voltage appears across this very small region. As a result, there is a very strong field inside, electric field inside, which results into a condition which is called the saturation velocity. The carriers drift with saturation velocity under this very strong field, and as a result, the current gets saturated. That was the reason. And why the saturation takes place? The reason is simply that, which I mentioned in the earlier class. So please take this particular correction, which I just, by mistake, I wrote plus here, and there was a confusion in the class, in the last class. It should be corrected that the borderline between that saturation and triode or linear region of the driver transistor is VO is equal to VI minus VT. When VO exceeds this, the driver is in saturation, and when it is less than this, the driver is in the triode. Therefore, the next thing is, if the driver in linear region, linear or non-saturation region, this is quantified by the fact that VO must be less than equal to VI minus VT. And of course, always I have to ensure that VI should be greater than equal to VT. This condition is common for both. This condition is common for both. Input gate voltage should be above threshold voltage, otherwise the transistor will not be on. We have to keep the transistor on. Okay? So it is greater than equal to VT, but at the same time VO should be less than or equal to VI minus VT. So the border between linear and saturated driver is simply set by the condition that VO is equal to VI minus VT. And you remember that we got two equations for the output. One is VO is equal to, let me rewrite, VDD minus 1 minus square root of beta R VT minus root over beta R VI. This relation is valid for the first case, for which VO is greater than equal to VI minus VT. This is valid under that condition. Whereas for the other case, we wrote, of course, an equation which is in the quadratic form. Let me rewrite 1 plus beta R U square minus 2 1 plus beta R W U plus 1 is equal to 0. I have to solve this equation. This is valid for the situation that VO is less than equal to VI minus VT, where U and W are normalized output and input respectively. So U is given by, as you remember, is given by we defined U as, VO by VOH, okay? And W was given by VI divided by VI, okay? W is equal to VI minus VT divided by VOH. Please note that VOH is equal to, what is VOH? VOH is equal to, yes, that is equal to VDD minus VT. That was the relationship. So we know that what I asked you in the last class, that using these two relations, this one and this one, relation number maybe I call it now A and I call this B. This is a straightforward relation between output and input, which is a linear relation. So when for VO exceeding this, when output voltage exceeds VI minus VT, output is just linearly related. That means it falls linearly with VI with a slope of root over minus beta R. It is clear from there. On the other hand, to get the relationship for the other region when VO output voltage is less than VI minus VT, you have to solve this quadratic equation to obtain, and naturally you have to reject, you'll find that there are two roots and one root is not practically feasible. So I think you have done that. I have asked you to do that. And by combining these two, we can now really plot the output input characteristics of a nMOS inverter under any condition. I have given you some problems in the last class where I mentioned the values of VDD and I think the value of beta R and some such thing, some such VT, threshold voltage, etc. And I asked you just to plot it numerically by writing down. It's either you can, it is not necessary to write a computer program for that. You can just use a just calculator and do that. But if you write down a computer program, the advantage is you can do this thing for any sets. You can generate the plots for any arbitrary choice for, and that's how I ask you to see that how important the effect of beta R is. I think you have seen that if you have a very large beta R, the large value of the beta ratio, the W by L of driver with respect to the W by L of the load, if you take a large value of that, naturally the characteristics become very sharp. Similarly, you should also note that the choice of VT is equally important. I have told you that I ask you to compute the values of from the plots. I ask you to calculate the values of the noise margins. So our effort should be to maximize these noise margins and to bring them of the same order. Their values should be very similar, very close to each other. So I should have almost equal noise margins for the low and high states. Simultaneously, I should also have a very largest possible values for them. That means that is possible only when when the beta R, the beta ratio is maximized. In fact, you will find that beta ratio of around 100 will give you the best result, even not 50. But it becomes so tardy. In fact, what happens in that case, the size of the transistor becomes so big that it is impractical for a VLSI. This point I told you in the last class. Then the question I also ask you to find out the values of the VOH is simply obtained, simply VDD minus VT. What about the VOL? VOL, in that case, either you have to solve this equation and make a more, it is not that analytically simple. It is little bit analytically complex. But there is an alternative approach to get the value of VOL simplistically. That will not be very accurate, but by a simple thing, you can obtain an analytical value, an analytical expression for the low state output voltage. Let us see how it is conveyed. That is an approximate expression, approximate derivation of VOL. You see that when VO is equal to VOL, then driver is in linear region naturally, and driver can be, in that case, driver can be represented by a resistance which I can write RD is equal to 1 upon GDD, where GDD is the drain conductance of the driver transistor. And in this case, the driver current, which is given by beta D by 2 into VGS minus VT VDS minus VDS square. Please note that in this case VGS is VI and VDS is VO, from where we get GDD is equal to del of IDD del VDS VGS constant, and that is obtained as simply by differentiation VGS minus VT minus VDS, and in terms of actual parameters you can write it beta D into VI minus VT minus VO. Alright, so GDD is obtained like this, and for VO, which is equal to VOL, and that is very small compared to VI minus VT. When VO is equal to VOL, VOL is a very small voltage, and usually it will be very small compared to VI minus. So using this condition here, I can simplify GDD as beta D into simply VI minus VT. I have assumed that VI minus VT is large compared to VO, which is VOL. I am deriving VOL. So when VO is equal to VOL, it is really small compared to, VO is very small compared to VI minus VT. So it is simplified, and that is your simply 1 upon RD. So you see that when I am close to, when the output voltage is close to the VOL, the low state output voltage, the driver is in linear region, and in the linear region the driver transistor can be considered as an ordinary resistance of value RD given by 1 upon GDD. GDD is the drain conductance, in the linear region, you remember. And the drain conduction is simple expression for drain conductance when VO is equal to VOL may be obtained like this, which is simply beta D into Vi minus Vt. Alright? Then the load transistor current IDLL as before can be written as some, let me rewrite it like this, GML by 2 into VDD minus VT minus V naught. Load transistor is saturation where GML is given by beta L into okay. The expression, standard expression for drain current was, load current was beta L divided by 2 into VDD minus VT, that means VGS minus VT whole square for the load transistor. And for the load transistor, VGS is actually VGS and VD is the same, and that is given by VDD minus V naught. That I have already seen. So this expression has been simply rewritten like this for some analytical convenience. Nothing else I have done. Simply I have defined the term GML, and GML is related to beta L and the voltage parameters like this. There is nothing new I have done. Now what I will be doing now, using this equation, this is very important now. I can draw an equivalent circuit of the inverter when the transistor when the output voltage is close to the VOL. And looking at this expression, I can draw the equivalent circuit like this. For the inverter, you see that the load transistor has been replaced by a voltage source Vt and a resistance which is equal to, is given by 2 by GML. You just look at this equation, you get this circuit. Here the voltage is VO. So between these 2 points the voltage is VDD minus VO. And between these 2 points the voltage therefore is VDD minus VO minus VT, because we have put a potential source here. And then you look at this equation, automatically there is a series resistance whose value is 2 by GML. This is a simplistic approach for representing the inverter by a linear circuit. Okay, when the output voltage is equal to the VOL, the low state output voltage. Then now using this I can obtain a value of VOL. What is VOL? VOL is simply given by, and therefore VOL from this equation, from this thing, can be easily obtained as VDD minus VT into GML divided by GML plus twice GDD. VO is simply equal to VDD minus VT divided by this plus this into this potential drop, and which simplifies to this. And usually GML for typical for simplification only. Usually GML is small compared to GDD. The conductance of the load transistor, effective conductance of the load transistor is usually very small compared to the effective conductance of the drain transistor, because I am maintaining a very large beta ratio. The driver transistor has got a very large W by L compared to the load transistor. Naturally, therefore, the conductance of the driver transistor will be large compared to the conductance of the load transistor, and that is this condition is usually satisfied, and therefore VOL is further simplified to VDD minus VT into GML divided by twice GDD. And this equation can be used now to calculate the value of VOL with less difficulty. You know that for earlier you had to obtain the value of VOL, you had to do many things. I indicated in the last class. To obtain the value of VOL, which is very important, I have to get the values of VOL. VOH is obtained very simply, but VOL has to be obtained. Otherwise, I cannot compute the values of the noise margins. Very important for me. But now I have found an easier means to calculate, to compute the value of VOL from an equivalent circuit output. This will not be that accurate because I have made a lot of simplifications, but it serves practical purpose. Okay? It serves practical purpose. And ultimately, we can also make certain more simplifications, because for VO is small compared to VI minus VT, and GML therefore is approximately equal to beta L into VDD minus VT, and GDD is equal to approximately beta D into VI minus VT because of this particular condition. Therefore, VOL by VOH can be obtained approximately as twice beta R into VDD minus VT divided by. So I can obtain a still further simplified expression for output voltage normalized with respect to output low state voltage normalized with respect to the high state voltage, and the expression is this one. And this is a very significant expression. You see that I have to minimize the value to improve the noise margin. I have to reduce the value of VOL. VOH is somehow, you know that once the VDD is chosen, once the VT is chosen, VOH is known, VDD minus VT. But VOL can be minimized simply, you see that, by increasing again the beta ratio. And that is expected. If you have a high beta ratio, the VOL will be less. And this is a very simple expression for VOL. One can compute VOL very easily using this particular expression, which is more or less valid for under practical consideration. So you note therefore that VOL is proportional to 1 upon beta R. Higher is the value of beta R, lower is the value of VOL. Okay, so this is a conclusion. Now you note that the slope of the VO versus VI curve, which is called the transition gain, is nothing but the gain. When you use the NAND gate, if you want to use it as an amplifier, so this is the gain in the transition region, and is given by simply root over minus beta R when driver in saturation this is a very important thing. I want a very high transition gain. If you have a very high transition gain, then only your characteristic will be very sharp, and you will be able to maximize the values of the noise margins. So I have to again beta has to be made high, not only from a very not only to achieve a very low value of VOL, but also to achieve a very high transition gain. Again, this dVo dVi is given by minus twice, you can easily derive it from the earlier expressions, divided by 1 minus when driver in linear region. And which is approximately given by minus twice beta r into u square if u, which is equal to VO by VOH, is less than 1. So when the output voltage is near the low state voltage, U very less compared to 1 means when the output voltage is near the low state voltage. That means when the driver transistor is in linear region. You remember, whenever output voltage is low, the driver transistor goes into linear region. So when the driver transistor is in deeply linear region, then the transition gain is found to be proportional to, again, beta r. Higher is the value of the beta r, this gain will be more. But as U gradually decreases, U means output voltage gradually decreases, this gain also decreases. So you see that we have observed two facts from these two. But there are three facts from this equation, and this equation. This equation says the higher is the value of beta r, less will be the value of VOL, and therefore higher will be the logic swing. More improved will be the noise margin. Again, this equation says that when the output voltage is close to the high state, when the output voltage is close to the high state voltage VOH, just beyond that, there is a very sharp fall of output voltage with increasing input voltage. And the rate of fall, that means which is called transition gain, again is proportional to beta r. Higher is the beta r, sharper will be that fall. And thirdly, we notice that this fall of output voltage with respect to input voltage, the rate of fall, when the output voltage is very low, that means we are close to the low state output voltage, again this gain also is proportional to beta r, but it is proportional to square root of beta r, it is proportional to beta r, very important. But the gain finally decreases to 0, practically 0, when U approaches, U is output voltage, when U approaches 0. Therefore, combining these three facts, we can now have a qualitative picture of the output versus input characteristics of the inverter. Let us try to draw that. This is my VO and this is my VI. 0, 0. Okay? You see that VOL and VIL are the same, which I've already told you, don't get confused. VIL must be equal to VOL and VIH must be equal to VOL to satisfy the input-output compatibility condition. So when I write VOL, it is also VIL. When I write VOH, it is also VIH. Please note, there should not be any confusion. Now you look at this characteristic now. This I have done for a particular value of beta R. Beta R is constant for a particular value of beta R. You see that for input voltage from 0 to Vt, the driver transistor is off. When the input voltage is up to Vt, less than Vt, the driver transistor is off, and therefore the output voltage should be maximum, and that will be equal to VDD minus Vt, which is my VOH. Thereafter, as Vi increases, you see that there is a linear fall. Initially the asymptote is linear. It is a linear asymptote. If I plot it, it is a straight line. So this region is which one? The region when the driver transistor is in saturation. Am I correct? And we have found that on saturation region, the output-input relationship is linear with a negative slope. And the slope of this is simply equal to minus root over beta R. Higher is the beta R, steeper will be the slope. Then as we, somewhere here, intermediate, somewhere here, I satisfy the borderline condition, which is the, what is that borderline condition? VO is equal to VI minus VT. This is what is called borderline condition. The corresponding, this is the corresponding VI and this is the corresponding VO, which separates the two regions for which the driver transistor in saturation and is in linear region. And I asked to compute these values also. You know, last time I gave you some expressions. And using those expressions, I ask you to compute those values. All right? Now, as you are exceeding this region, as you go to the right of this region, when Vi, you can call it Vi naught, and you can call it Vo naught, this is a borderline. As Vi exceeds that Vi naught, the driver passes into linear region. And you have noted under that condition, the gain is the transition dVo dVi is equal to minus 2 beta R into U being the output voltage itself, normalized output voltage. And you see that the slope is gradually decreasing with increasing U. And ultimately it must be 0. That means this is the differential, the slope should be 0. And somewhere that is reflected there in that. And somewhere here perhaps I will get a point where the slope is unity. Somewhere here I will get a point where the slope is, this is the unity gain, unity slope. And from this point to this, whatever I call, I get, what is this called? Noise margin in the output 0 state or input high state, whatever you call it. There are two ways of defining this. So this is my noise margin for the output 0 state. It is VOH minus that point where the gain, minus the input voltage, where the gain is unity, slope is unity. And if you come to the other side, what is the value of the noise margin? It will start from this point naturally. 0 to or from, no, it will start from this same point. This is your VIH. VIL, which is the same as VOL. From this point, can you find out some unity gain point here? Because here our analysis was such that we have found that as we exit this point, it is a linear slope. Because our analysis was a little bit simplistic. Actually, there will be a round off here. Actual, most practical case, you will find a roll off or round off at this point. And therefore, you can always identify a point where the gain is unity. But for practical point of view, it is not necessary. Actually, the noise margin is simply this, which is Vt minus VIL or VOL. That is your noise margin in the one state. In a NM0 state and one state. Output one state and output one state. So noise margin in the one state is entirely controlled by the threshold voltage. You just check. And definitely VIL. That is why you have to see such that Vt should not be too low. If Vt is low, what will happen? The noise margin, the NM1 will be affected. And I have to have it as low as possible value of VIL. That means I have to have a very high beta R. So to optimize the value of NM1, I have to choose Vt appropriately, as well as I have to choose the value of beta R. That means I have to maximize beta R as far as practicable. As far as practicable. On the other hand, to obtain a high NM0, you see that there is a little reverse thing. You see that if your Vt is large, you are unnecessarily eating off some portion of output swing. Where otherwise, I expected the output swing will go up to VDD. The output should go up to VDD, but it cannot go up to VDD in the NELS configuration. It goes up to VDD minus Vt. Increasing the value of Vt will lower that, though it will improve the noise margin 1. It will deteriorate the value, degrade the value of NM0. And that I can little bit manage better by increasing the value of beta R, because increasing the beta R value, it will create a shape like that. I am coming to that now. Say, if I am plotting 3 more curves. Maybe for the three curves, the beta R values may be like this. For this one, beta R may be, say, 10. For this curve, beta R may be 20. Whereas for the last curve, beta R may be, say, 60. Can you see it clearly? You see that taking higher values of beta R, I cannot control anything so far as NM1 is concerned. NM1 is entirely controlled by, is it correct? Having a higher value of beta R, I cannot have any no, there is a little control, little control, because the value of this VIL will be reduced. Why it is more important is the choice of Vt. So you see that Vt choice, neither it should be too high, nor it should be too low. And one has to make a very optimum choice of the value of Vt along with the value of beta R. Both are very, very important parameters in a MOS inverter. So I want to emphasize on that. In a NELS, an inverter with saturated load, a single channel inverter, it may be NELS, it may be PLS, it depends on it is N channel or P channel, does not matter. If it is a single channel inverter where the load is in saturation, both load and driver are enhancement mode devices, and load is permanently kept in saturation under that condition. You see that if you want to improve upon, if you want to optimize the output-input relationship, it's very important for logic applications, then I have to choose the values of threshold voltage and the beta ratio very, very appropriately. So this is our conclusion. And from this discussions, whatever we have followed so far, we have now have a tool, in fact, it's a mathematical weapon to handle these things. If I want to do it precisely, I can do it by writing those equations and writing a small program or using a calculator. I think I will expect that you will all, or most of you will write a small computer program and check how it works. It's a very interesting thing. And on the other hand, I have also given an analytical tool, a simplistic analytical tool to calculate the values of VOL quickly, as well as to calculate the values of the gains. If you know the values of the gains, you can also find these plots. There is no need on to going in detail, because from the gain slope you can get the actual plot. If you know the slope, how it varies, you can also obtain the actual plots. The slope expressions are rather simple. You have already noted. Slope expressions are rather simple. So one can find out these plots of the inverter characteristics, which is very, very important. And one thing comes to us now. It is, we might conclude by saying that a MOS inverter is very much dependent on geometry. The performance of a MOS inverter is very much dependent on layout geometry. Layout, threshold voltage, etc. I can design and it will be constant for all the devices. But then we can play with the geometry. Geometry plays a very important role to control the characteristics of the inverter. And such inverters are normally, the way we know that such inverters are called ratioed inverters. And any logic which is designed using such inverters are normally called ratioed logic. Ratioed logic. And you'll come to know afterward that we normally refer to two kinds of logics. One, so far as MOS logic is concerned, one is called ratioed logic, where this ratio of beta R is very important. The other is called ratio-less logic. So we shall be discussing that gradually, what is meant by ratio-less and how it is important. We shall see that most of the logics which are used today in practical circuit, they are dynamic logics and they're not static logics. And this dynamic logics normally use ratio-less logic, ultimately which leads to a very high packing density. All right? So I'll stop now. After some time I'll stay in the second class.